Now, the stuff that we have in the wall that we plug things into is not direct current, it's actually alternating current. And the reasons that it's alternating current are really interesting, and we're going to be talking about them later when we talk about how electricity is generated. But for now, alternating current changes direction at regular intervals. Many electrical components, such as incandescent light bulbs, function regardless of the direction of the current. As long as electrons are moving through the circuit, it does not matter whether they're moving continuously in one direction or alternating between directions. So here in figure 7, we see that in alternating current, electrons accelerate back and forth around an average position as the voltage in the wire alternates. So the voltage in the wire alternates so that basically one end of the wire is positive and the other end of the wire is negative. And then when it alternates the other way, the first end of the wire is negative and the other end is positive. Another way to think about this is to think about the wave of alternating current. We've been talking about waves. So alternating current looks like this. There's a time when the electrons are moving in one direction, and then they move in the opposite direction, and then in the first direction, and back and forth. And in the kind of alternating current that we use, this happens 60 times a second. So the frequency of this is 60 hertz. This switching back and forth happens 60 times a second. Recall that electrons follow an erratic path, but in the presence of an electric field, the net movement of electrons is in one direction. The net movement of electrons alternates in an alternating current. First they go one way, and then they go the other way. Okay. This high frequency change of direction, high frequency, it's not that high, it's 60 hertz, 60 times a second. This high frequency change of direction means that individual electrons actually travel very little. Rather, it can be more appropriate to say that they wiggle back and forth. So, explain. Batteries discharge electric current. Wall outlets are a source of alternating current. Why might the adapter shown in figure 8 between the wall outlet and the laptop computer be necessary? Oh, here's a big fat hint. It tells us in the picture. The laptop battery requires an adapter to convert alternating current to direct current. And what happens when the battery is unplugged, right? I mean, when the computer is unplugged, then it's running off of direct current. So what's happening here is that alternating current from the wall is getting converted into direct current by the adapter. And sometimes you see, by the way, this symbol. Let me try to draw it here. You see a symbol, here's the best way to do it. You see a symbol that looks like this to indicate alternating current. A straight line and then a series of dashes. This indicates alternating current. And back over here, I don't know what happened to my nice alternating current here. You often see a symbol that looks like that. That indicates alternating current. There we go. Okay, so now you know what to write in this space here. I'm just reading these things as I go along. Evidence notebook. As an electric generator, and electric generators such as the one in the UNIT project, transforms mechanical energy into electrical energy. Does the type of current produced by a generator matter? Definitely does matter. Consider the motion of an individual electron in an electric field in a metal wire. Why does the electron move the way it does? We've definitely been talking about that stuff. So here we have a cool looking toy. A charge moving through an electric field can be compared to an object falling due to the influence of a gravitational field. See, there are those two words again, electric field and gravitational field. The potential energy of a ball on a track, shown in figure 9, depends on the height difference between the top and the bottom of the track. The ball has a tendency to move from a position of higher potential energy, up here, to a position of lower potential energy down here in this box. Higher potential energy to lower potential energy. In a battery, the potential energy of a charge depends on the difference in electric potential. So, explain. Compare the ball and track shown in figure 9 to a charged particle moving through an electric field. What could the track represent? Ooh, that's a good one. What could the track represent? Okay, I think we're gonna, let me just look ahead here. We're just gonna read through generating current and then we're gonna stop for this section. A difference in electrical potential energy produces an electric field. A difference in electrical potential energy produces an electric field. When the positive and negative terminals of a battery are connected by a wire, the electric field in the wire accelerates electrons through the wire, although not that fast, right? We're talking electron drift here, generating an electric current. This current can be measured using a device called an ammeter, or visualized using a component such as an incandescent light bulb. And we have both of those things in this diagram down here. An incandescent bulb glows brighter when more current is in the filament of a bulb. And by the way, what's really going on here with this glows brighter, more current thing? You already know this. You know that a lot of you keep the brightness on your cell phone or your iPad or your Chromebook turned way down so that the device doesn't use too much battery. It doesn't use your battery too fast. That's because the brighter it is, the more energy it's using. And so if you turn the energy down to save energy, it's not as bright. The screen is not as bright. Same exact deal down here. We could think of this being a cell phone instead of an incandescent light bulb. In figure 10, the circuit on the right has a battery with twice the voltage of the battery on the left. Okay, down here it says the voltage of the battery on the right is 3 volts. The voltage of the battery on the left is 1.5 volts. So the battery on the right is has two times the voltage of the battery on the left. The ammeter shows that the circuit on the right has double the current compared to the circuit on the left. So this is actually kind of hard to read here, but the pointer is pointing at 2 here, and on the right, and the pointer is pointing at 1 on the left. So the 3-volt battery is producing 2 amps of current, and the 1.5-volt battery is producing 1 amp of current. So let's analyze. Compare the voltage and current of the two circuits shown in figure 10. We were just talking about these two circuits up here and how the one on the left has a 1.5 volt battery and has 1 amp of current moving through it, and the one on the right has a 3 volt battery and has a 2 amp current moving through it. Assuming the pattern holds for other circuits, what is the relationship between current and voltage in a circuit? Now, I should say that we use the abbreviation V for voltage, And for current, we use the letter capital I. So for a direct square relationship, that is a direct square proportionality, this is what that would look like. This says V is proportional to I squared. And for an inverse proportion, that would look like, that would look like this right here. V is proportional to 1 over I squared. For an inverse square, got that backwards. For an inverse square proportion, that's what V is proportional to 1 over I squared. For just a regular inverse proportion, that looks like this. V is proportional to 1 over I. And for a direct proportion, V is proportional to I. So think about it. The current in a circuit depends on the voltage of its energy source. The higher the voltage, the greater the difference in potential energy of each electron between the two terminals of the battery. The greater the difference in potential energy, the stronger the electric field produced. An electron at the negative terminal of a battery will be accelerated through the wire toward the positive terminal by this field. As the electron moves, it repels other electrons in front of it. The direction of the electron changes when it collides with other particles, but the electric field causes all of the electrons in the field to drift in the same direction as they move. When the field strength in the circuit increases, the drift velocity of the electrons increases. As the drift velocity increases, the current increases. Okay, so you're supposed to use this information here and what I just told you to answer this question up here. And we're going to stop there, and we're going to do a little lab project next time.